Hello, this is Dr. Jambitsky and welcome to my environmental science screencast. Today we are going to talk about the pH of our environment. Hello and welcome to our discussion. So today we will talk about water. Water is very important part of our environment. We do have shortage of fresh water supplies because most water on the planet is in the ocean. So very frequently water is called the blue gold. And today we will discuss one very important property of water, which is called pH, and it is written as a small p as a capital H, and we will discuss why. So this is a very important property of water. Using pH, we can monitor water quality, and that would be true for drinking water, or we can also monitor water quality in a private swimming pool or public swimming pool, or we can even monitor water quality in an aquarium, either an aquarium that you have at home or a big aquarium, such as, for example, New Jersey State Aquarium. So let's learn about pH. So I made some notes for you so you can follow along, and if you would like to write something down, feel free to pause the video and copy the screen. And this is actually a great advantage of the video, that you actually have everything at your fingertips. Alright, so we are talking today about a very important property of water, which is called pH. So let's take a look at it. So P, which is a small p, not a capital P, stands for potential, and H, which is capital H, is standing for hydrogen. So pretty much pH is hydrogen potential, if you would like to say it this way. But most of the time, we just call it pH. We are familiar with the molecule of water already. So this is a molecule which is made of 2 hydrogen atoms and 1 oxygen atom. So this is a compound because water is made of 2 different elements. Those atoms are held together by covalent bonds, and we know that what we see here on the screen is called the molecular formula of water, that tells us how many atoms do we have of which kind. So water molecule is very interesting because it is capable of a quite peculiar process which is called dissociation. So let me write it down for you. Dissociation. Alright, dissociation is obviously a noun. This is a noun, so I'm gonna put letter N, and the verb from the word dissociation would be to dissociate, right? Which means to undergo dissociation. So water can dissociate, right? And it's written for you right here. So what does it mean water can dissociate, or what does it mean dissociation in general? So let's talk about it. So molecule of water can dissociate by breaking into ions. So when a molecule breaks to produce ions, this is what we call dissociation. And it's very interesting that this is what we have. So this is your molecule of water, and when it dissociates, it gives us ions. One ion is like this, H+, and we already know that this is so-called hydrogen ion, which is also known as a proton. And the second ion is new for us, so that's the first time we see it. It's written like this, OH with a minus. So you remember the structure of the hydrogen ion that only has a proton and no electron. We have already looked at the structure of hydrogen ion, and if you forgot, obviously it's a good idea to replace the screencast that we had in the past. But here, this is our hydrogen ion, H, with a positive charge, and the second ion, which is called hydroxyl ion, and sometimes it's also called hydroxide ion. These two words are kind of interchangeable, and it's written as OH with a minus. So it's quite interesting ion because unlike hydrogen ion, it's actually made of two atoms. One is oxygen and another one hydrogen, and this combination of two atoms still has a negative charge, OH minus. So when water dissociates, it gives us these two ions. One ion is going to be hydrogen ion with a plus, and the second ion is going to be hydroxyl or hydroxide ion with a minus. And now I'm back to my original picture here, where I'm looking at the glass of water. So let's think about it. So in a glass of water, I still primarily have molecules of water, H2O. And I will have just a little bit of hydrogen and hydroxyl ions. Very, very, very small percentage of water molecules dissociate. Most of the water molecules are still H2O, but very, very small percentage will dissociate and will give us hydrogen ions and hydroxide ions. Alright, so water molecule will dissociate in a very small percentage to give us these two ions, hydrogen ion and hydroxyl ion. Now, so let me do a brief introduction to terminology here, which is very simple, but we have to be comfortable with this. So if we place a chemical symbol like this inside of the square brackets, that means concentration. So for example, if I'm going to place H plus inside of the square brackets, so what does it mean? It means concentration of hydrogen ions. This is what it is, right? Now, if I'm going to place OH minus inside of square brackets, what does that mean? That means concentration of hydroxide ions, right? So anything inside of square brackets will be concentration, right? So concentration tells us how much of a particular chemical we have in water. So for example, let's see, you are going to dissolve sugar in a glass of water, and you're going to put 1 teaspoon of sugar and you're going to swirl it, right? And you will have a solution of sugar in water. But if you are going to put 2 teaspoons of sugar, and again you're going to dissolve it, your solution of sugar will be more concentrated, because now you have 2 teaspoons of sugar dissolved compared to the 1 teaspoon in your original solution, right? So concentration tells us how much of a particular chemical would be dissolved in water. And so we need to kind of understand the difference between the ways how we can write here. So if we just write like this, H plus, this means just hydrogen ion, right? But if we are going to put H plus inside of square brackets, that becomes concentration of hydrogen ions. All right, makes sense? So what is pH? So there is actually a strict scientific definition of pH, which is over here, and there is a formula how pH can be calculated. All right, so pH is equal to the negative logarithm of concentration of hydrogen ions. So if you took elementary algebra at high school or in college, you know that logarithm is a mathematical function. So pH is related to concentration of hydrogen ions and tells us how concentrated they are. And to calculate the pH, we have to take negative logarithm of concentration of hydrogen ions with a negative sign. Very exciting. Well, you know, when I talk about this during an in-person class, many students begin to worry, right? Because, oh, elementary algebra, this is so difficult. I cannot possibly handle this, right? But on the good side, actually, we do not use this formula to calculate pH in real life very often. There are other ways how we can measure pH even at home if you would like to monitor the water quality of your in-ground swimming pool. And there are two main ways how pH can be measured practically without using this formula with a logarithm. And I have shown these two ways for you over here. So let's take a look how we can measure pH. All right, so to measure pH, so here's our pH. We can use two main approaches. Okay, number one and number two that I have shown you. So the first approach will need a piece of equipment which is called pH meter. So a pH meter is a machine, a device, a piece of equipment that could be of different size depending on how sophisticated and expensive it is. But in a nutshell, pH meter will have a probe that you can actually submerge in water or any type of solution, and this machine actually has this formula that looks scary, right? To some of you, this machine has this formula built in, and so the pH meter is going to calculate the number for pH and will just display it on the screen, so we don't have to worry about the formula with logarithm. Well, this is the first way how to measure pH is to use pH meter. And the second way is to use indicator paper or indicator dye. What is an indicator? Indicator is a chemical that can change colors depending on pH. So it's like a chameleon dye, right? So if pH has certain number, then this indicator dye will be of certain color. Now, the indicator paper is treated with indicator dye, and if you have a strip of indicator paper, you can again dip it in water or any kind of solution, take it out, and then there will be a color chart. You are going to align your strip of paper with the color chart and compare the colors, and you will read the number from that chart. So this is a little bit less expensive, less sophisticated way. It's probably not as precise as the pH meter technique, but it works. And, if you have to measure the quality of water of your in-ground swimming pool, you can go to Home Depot and get water quality testing kit, and it probably will have strips of indicator paper. Right? So these are the two main ways how we can measure pH without using this formula, by using either pH meter or indicate people. So now I do want you to kind of know about this formula for testing purposes, so you have some idea, how a pH is calculated. However, I will not ask you to use this formula, all right? Just have an idea that pH is a negative logarithm, and what is most important, it's a negative logarithm of what? Of concentration of hydrogen ions, because H is inside of the square bracket. Very well. All right, so I have a little bit more notes for you over here. And so we will start with an idea of the pH scale. So pH can be high or low, so it shall have some type of a number associated with it. So the pH scale ranges from 0 to 14. So what does it mean? So the pH cannot be negative. The lowest number for pH is a 0, and it cannot be more than 14, cannot be 15. So the pH scale is from 0 to 14. Now, this is also very important. When we measure pH, and if pH is exactly 7, what does it mean? We say that solution to be neutral. So pH 7 is neutral. 7 is right in the middle between 0 and 14. Now, if pH is less than 7, we will say that solution is acidic, right? So, for example, pH 5 will be acidic. Now, if pH is greater than 7, so we are going to say that solution is basic, or we can say that solution is alkaline. Basic and alkaline, these two words are interchangeable. All right, so now we know that the solution can be alkaline. For example, if pH is 9, which is greater than 7. And so what I did over here, I made a picture for you. So I kind of draw the pH scale, which ranges from 0 to 14. I showed you that 7 is right in the middle, and we already know when pH is exactly 7, we say the pH is neutral. Now, if pH is less than 7, any number which is less than 7 will be between 0 and 7. Then pH is going to be acidic, solution will be acidic. And now if pH is greater than 7, somewhere between 7 and 14, we are going to say that this is a basic solution or alkaline solution, and pH is basic or alkaline. So let's take a look at some examples. So as a matter of fact, in your textbook, we have a pH diagram, a chart, that help us to see some examples of pH. So let's take a look. So this chart is pretty much similar to what I had for you on the screen, but in your textbook it is shown in a vertical direction rather than horizontal direction, but it's still the same. This is pH 7, which is actually the pH of pure water, and it is neutral. So pH 0 is over here, is very acidic, right? And pH which is 14 over here at the bottom is very, very basic or very, very alkaline, right? So pH which is greater than 7 is basic, and pH which is less than 7 is acidic. Now, it's also important to see here that the more I'm getting away from 7, the more severe pH becomes. So if I'm moving from 7 to 6 to 5 to 4, etc., the pH becomes more acidic and more acidic and more acidic and more acidic, etc. So, for example, if you look at the pH of pure water, you know that, for example, coffee is more acidic, but the battery acid is even more acidic than coffee by itself, right? The same thing if I'm moving in this direction. If I'm moving more away from 7 and closer to 14, the solution becomes more and more basic, right? For example, if I'm comparing the seawater with pH 8 to, let's say, soap with pH 12, obviously soap will be more basic compared to the seawater, right? And here we are looking at the liquid soap. All right, so what I did for you over here on this slide, I took some examples from the chart that we just observed, and I also added a few examples of my own. So let's take a look. So, for example, so pH of lemon juice is 2. All right, so what kind of pH is pH 2? We are going to write it like this, pH equal to 2. So obviously it's going to be in this range. It is less than 7, so we can say that lemon juice has acidic pH. Now, another example that I have here is ocean water. So I already mentioned this, that the pH of ocean water is 8. So this can be written as small p capital H equal to 8. And this number is greater than 7, so we can say that ocean water has basic pH or alkaline pH. This is actually very important because all aquatic life in the ocean is adapted to this basic pH of 8. And when we have human activities and we pollute the ocean, we dump chemicals or plastics in the ocean, or we also change the composition of the air that surrounds the ocean, the pH of the ocean also can be changed by humans, and it can become less basic. This can be very detrimental and damaging to many kinds of marine creatures that cannot survive if pH of the ocean water is less basic. And we will come back to this idea in a little bit. All right, so please remember that ocean water has a pH of 8, which is basic. So obviously it's not as basic as bleach or soap, right? But it is still greater than 7. And I also have this example, and I frequently ask the same question during my in-person class. So pH of human blood is 7.4, and so when I ask this question in class, what kind of pH is 7.4? This is a pH of human blood. So students say it's neutral, but actually is not, because 7.4 is greater than 7. So, and if pH is greater than 7, it has to be basic or alkaline, right? So we can write it like this, small p capital H equal to 7.4. So just a little bit over 7, so we can say that this pH is slightly basic or slightly alkaline. All right, does it make sense? So the pH of human blood is a very important number. So if pH becomes too much deviated from 7.4, the person can get sick and even lose their consciousness. So, for example, if a person is admitted to the emergency room in the state of unconsciousness, one of the first tests that the ER doctor will do is to test the blood pH. And very frequently, wrong blood pH, especially when pH drops, the person can become unconscious. This is very frequently happens in patients with uncontrolled diabetes, who missed their insulin injection, for example. And if the level of sugar is elevated, the blood pH can drop, and it can become substantially less than 7.4. So in medicine, we call this diabetic ketoacidosis. And if diabetic ketoacidosis is very, very profound, obviously the person can lose their consciousness, and we call this diabetic coma. Right, so let me write it for you. Diabetic coma. This is when a patient with diabetes is unconscious in the state of coma because their pH of blood is too acidic. All right, so I hope you can appreciate now the importance of pH for human life, right? And this is just one example. And to understand the power of the pH scale, I would like to show you how the ions of hydrogen and hydroxide are related to one another. So we will discuss the ratio between these two ions, because remember, water molecule breaks to form these two ions, the hydrogen ion and the hydroxide ion. So let's take a look here. So I'm going to zoom in a little bit. All right, so again, for you to discuss the ratio between H plus and OH minus ions, I draw the pH scale. So let's take a look. So remember, the pH ranges from 0 to 14. The pH cannot be 15. The maximum number is 14. The pH cannot be negative. The smaller number is 0. 7 is right in the middle. We remember that pH of exactly 7, this is pH of pure water, is called neutral pH. And it's very important to know that when pH is exactly 7, then concentration of hydrogen ions would be equal to concentration of hydroxide ions. So they are present in like 50-50 ratio, right? So they are equally concentrated. Now, if I'm going to move away from 7, my ratio will change, and one of those ions will become more concentrated, and another will become less concentrated, right? Remember, at pH 7, they are present in equal concentration. So, for example, acidic pH, which is shown here in red color, would include any numbers which are less than 7, 6, 5, etc. Now, if pH is acidic, then my hydrogen ions are more concentrated compared to hydroxide ions. And you remember from, elementary math that this symbol means greater than. So concentration, remember the square brackets, concentration of hydrogen ions is greater than concentration of hydroxide ions. And just think about it. Remember, if I'm moving more away from 7 in this direction, pH becomes more and more acidic. And what's going to happen, I will have more and more and more and more of hydrogen ions. And I will have less and less and less and less as I'm moving away from 7 of hydroxide ions. And when pH is 0, I will mostly have hydrogen ions and almost no hydroxide ions. Now, the next logical question would be, what's going to happen if I will move my pH scale in the opposite direction from 7 to 14 when I'm going to enter the basic or alkaline pH, which is shown here in blue column? In this case, I will have the opposite scenario. So concentration of hydrogen ions will be less than the concentration of hydroxide ions, as indicated by this symbol, which means less than. And again, the very same thing will happen. The more away I will move from 7 to 8, 9, 10, etc., all the way to 14, I will have more and more and more of my hydroxide ions, which are in blue, and I will have less and less and less of my hydrogen ions, which are in red. And when my pH is at 14, I will mostly have OH minus ions and almost no hydrogen ions. Right, so as you can see here, for the basic pH, the scenario would be opposite to that of the acidic pH. And I understand that this explanation requires some thinking and some processing, so what I would recommend, you can rewind the screencast and listen to this explanation one more time and think about it. Alright, so now we know what is the ratio between H plus and OH minus ions. And the next thing that I would like you to understand is how powerful pH scale is. So let's take a look over here. So at my notes. So if I'm gonna change pH by 1 unit of pH, how I will change concentration of ions, and what ions we are talking about here, H plus and OH minus. So I'm gonna move 1 unit of pH, and then the concentration of my ions is gonna change tenfold. All right, 1 unit of pH gives me 10 times difference. It's a very, very powerful move. Now, what about moving 2 units of pH? So if I'm gonna move 2 units of pH, for example, from 7 to 8 and to 9, right? From 7 to 9, 2 units of pH. In this case, I'm gonna change my ion concentration 100 times, because 10 times 10 is 100. Now, what do you think will happen if I'm gonna move 3 units of pH? So for example, from 7 to 8, from 8 to 9, and from 9 to 10. These are 3 units of pH. In this particular case, I'm gonna change the concentration of ions 1000 times, right? So I'm multiplying this change by another 10. 10 times 10 times 10 is 1000. Now, what about if I'm moving 4 units of pH? For example, from 7 to 8, from 8 to 9, from 9 to 10, from 10 to 11. This would be 4 units of pH. In this particular case, I'm going to change concentration of my ions 10,000 times, right? Isn't it amazing? So each time I'm using 1 unit of pH, I'm changing concentration tenfold. If I move 1 more unit of pH, it's going to be 100-fold, etc., etc., etc. This makes my pH scale extremely, extremely powerful. So once again, it is useful to rewind the video and listen to this explanation one more time if you didn't get it. Now we are going to take a look at this chart one more time, our pH scale, and that's exactly repeats what we have already discussed. So here I have concentration of hydrogen ions compared to distilled water, which is pure water, right? So if I'm moving from 7 to 6, I'm gonna have 10 times more of hydrogen ions. If I'm gonna move from 7 to 6 and to 5, if I'm gonna compare 7 pH to 5 pH, this is 100 times difference, right? Etc., etc. Now, if I'm going to move in this direction, I will reduce concentration of hydrogen ions because I will have less hydrogen ions but more hydroxide ions. And that's why, because they're talking here about concentration of hydrogen ions, I will have 1/10, 100, etc., 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 right? So what happened to my hydrogen ions and what happens to my hydroxide ions would be the opposite. So when I move in this direction, I'm reducing concentration of hydrogen ions tenfold, another tenfold, another tenfold, but I'm increasing the concentration of hydroxide ions, right? Because the scenario is opposite. So to make it a little bit easier for us, let's try to practice and let's review some questions that I could ask you during the lab or on the quiz or exam. So very frequently I am giving you two numbers of pH. For example, over here I have pH 7, which is a pH of pure water, and pH of 8, which is the pH of ocean water. And I will ask questions, something like this. Okay, so let's take a look. Like, which pH is more acidic, right? Is pure water more acidic or ocean water more acidic? Remember, the lower is the pH, the more acidic the solution is, right? So pure water is the correct answer. Pure water is more acidic than ocean water. Now, the second question, which pH is more alkaline, right? Alkaline or basic would be opposite to acidic. And if you think about it, you will correctly tell me that ocean water is more alkaline compared to pure water. So let's take a look at the next question here. Which pH has more hydrogen ions, right? Will pure water have more hydrogen ions or ocean water will have more hydrogen ions? So remember, the lower is the pH, the more hydrogen ions we will have. All right, so the answer to this question would be pure water. Pure water will have more hydrogen ions compared to the ocean water. Okay, next question. So if I'm interested in hydroxide ions, which are going to be OH minus, I'm going to ask the same question. Which pH has more OH minus ions? Obviously, the more alkaline pH is, the more hydroxide ions it will have. So the correct answer is ocean water, because pH 8 will have more hydroxide ions compared to pH 7. And the next question, which is also quite easy but very important, how many times more? So for example, if I say that pure water has more hydrogen ions, H+, compared to ocean water, how many times more, right? How many units of pH do we have between 7 and 8? 1. 1 unit of pH is 10 times more. So my pure water will have 10 times more hydrogen ions. All right, does it make sense? Now, if I'm interested in the other ion here, so if I'm interested in hydroxide ion, how many times more of hydroxide ion I have in the ocean water compared to the pure water? Very similarly, it's going to be 10 times, right? 10 times. So ocean water will have 10 times more OH minus ions, and it will have 10 times less H plus ions compared to the pure water. Okay, does it make sense? Very good. All right, so let's take a look at another example here. All right, so once again, I'm taking those numbers from the charts that we observed before, and now I'm gonna compare soda, like Coke or Sprite or some type of soda, to pure water. And here are our numbers. So the pH of soda is 3, which is a lot more acidic, right, than a pH of pure water. And I have already answered the first question. What is more acidic? Soda is more acidic because remember, the less is the pH, the more acidic is the solution. And which is gonna be more alkaline or more basic? And the answer is opposite, right? So the greater is the pH, the more alkaline the solution is. So if I'm comparing soda to pure water, so in this case, pure water will be more alkaline. So the next question, which pH has more hydrogen ions? More acidic pH will have more hydrogen ions, so soda will have more hydrogen ions compared to that of pure water. Next question, which pH has more hydroxide ions? So the more alkaline pH is, the more hydroxide ions we will have. So the answer to this question, pure water will have more hydroxide ions compared to soda because it is more basic. And the next question, how many times more or how many times less? So to answer this question, we have to see how many units of pH would be between 3 and 7. And it's obviously 4, right? Because 7 minus 3 is 4. These are 4 units of pH. So how many times more or how many times less of a particular ion we will have if we are going to compare these two solutions, soda and pure water? And it's very easy to calculate because remember, so each time I'm moving 1 unit of pH, I'm gonna change the concentration of ions tenfold. Now here I am moving 4 units of pH between 3 and 7, so I have to multiply 10 by itself 4 times, which will give me a number with 4 zeros, right? So a number with 4 zeros is going to be 10,000 times. So if I'm going to compare soda and pure water, soda will have 10,000 times more of hydrogen ions, H+. It's 10,000 times more acidic compared to pure water, right? And that's why when we say, okay, is soda really good for you? And the answer is no. And because, first of all, it might have tons of sugar. If it is diet soda and it might not have really sugar, it is still pretty acidic. So, and it's probably not very healthy to drink straight acid. All right, and I have one more example over here. So I'm comparing here coffee and pure water. So let's see what we have here. So coffee has a pH of 5, and pure water has a pH of 7. So these are the important numbers we are going to work with. So let's take a look. So what is more acidic? So what is more acidic? The lower the pH, the more acidic something is. So because coffee has pH 5, coffee is more acidic than pure water. So the next question is, what is more alkaline? So the greater is the pH, the more alkaline or basic the solution is. So the answer is pure water. Pure water will be more alkaline compared to coffee. So the next question is, what will have more hydrogen ions? So more acidic solution will have more hydrogen ions. So coffee with pH 5 will have more hydrogen ions. how many times more? To answer this question, we need to know how many units of pH. We are looking here for comparison purposes. So between 5 and 7, we have 2 units of pH. So what we have to do, we have to multiply 10 by 10 because we have 2 units of pH. So, and the answer is going to be 100 times. So coffee will have 100 times more hydrogen ions compared to pure water. So the next question would be, what about the solution that has more hydroxide ions? So, and the answer to this question would be pure water, because 7 is more alkaline pH. So pure water will have very similarly 100 times more of OH minus ions. And also, please remember, so if the solution will have more of OH minus ions, it will have less of H plus ions, and the other way around. So for example, coffee will have 100 times more hydrogen ions compared to pure water, but it will have 100 times less hydroxide ions, OH minus, compared to pure water. So it's very simple and very elegant. All right, so what I recommend to do is maybe to write these questions down and look at our original chart with pH. This particular chart, which is from your textbook, and you can practice to answer this type of question. So for example, you can compare pure water to seawater, or pure water to baking soda, or you can compare tomato juice and lemon juice, right? And again, here we have 2 units of pH. Between tomato juice, pH is 4, and the lemon juice, pH is 2 units of pH. So it will be 100 times difference in concentration of ions here. So you can play with this table and, try to answer the questions that you saw in the prior screen. And that will help you to remember this material better. And I just wanted to correct myself here. So this is not really a table. I would say it's a chart, right? Or pH scale. So doesn't really look like table. Very well, so let's take a look at my next set of notes, and here we are going to discuss the difference between acids and bases. So in our environment, there are a variety of different chemicals, and some of those chemicals could be acids, and some of those chemicals can be bases. So what is the difference between acids and bases? So let's take a look. So here I have a definition of acids for you, and here I have the definition of bases. What exactly acids and bases are? Alright, so acids, as you can see over here, are chemicals that add hydrogen ions to water and decrease pH. The pH of acids is usually less than 7. At this time, I am going to pause, all right, and we will continue in the next screencast, so you have a little break. And so let's just remember that we stop at the definition of bases. So we're going to continue talking about acids and bases in our next screencast. So if you have any questions, you know how to get in touch with me. So I will be looking forward to your questions, and I will talk to you soon.